Okay, in this video, we're going to talk about first-order reactions. We've introduced kinetics and rate laws in the previous lecture, so go back and make sure you understand those concepts first. But we're going to use the rate law and move forward to discuss a particular type of rate law, a particular type of reaction that it corresponds to. And these are first-order reactions. So, I mean, we understand that we can write a reaction from reactants to products. It could look like A plus B goes to C plus D. But we know from previous lectures now that we can't just look at the reactants and say, we know the speed of this reaction, the kinetics depend both on A and B, and we don't know that they depend to the first order on A or to the second order on B. Those things have to be experimentally derived. But when you do the experiments, a lot of reactions fall into a couple different types of reaction orders. First order reactions or second order reactions are very common. So we're going to discuss first order reactions today, and then in the next lecture will be second order reactions. So some reactions, no matter what they look like when you write them and balance them overall, have rate laws that will only depend on a single reactant to the first power, and these are first order reactions. So I'll just write again here what's already written down below. Our rate law is always of the order rate equals K, and then some reactants here, okay? And usually we'll write each reactant, A, B in this case, C and D don't belong, and these will be to some exponents. Okay, here in a first order reaction, one of these will be 1, and one of these will be 0. And anything to the 0 is just 1 itself, so we don't have to write this. So the rate law ends up looking like this. A rate law will always be rate equals K times something, unless it's a 0th order, but we'll get to that down the road too. So here's first order, and it's first order because there's a power of 1 here. But that 1 is implied, we don't have to write it. So these are first order reactions. Now, from this equation, we can actually get something more quantitative that describes what our data and what our reaction should look like. Remember, this rate here is really a rate of change, right? And it's really negative, a change of this reactant over change in time. We defined that last time. And if you know something about calculus, which we're not going to require the full integration here, so don't be too alarmed, but this is essentially equivalent to dA dt. Negative dA dt is negative delta A delta t. So the change in A over the change in t. Now, if this is equal to this, then that represents an equation that we can integrate. And again, for the purposes of a course like general chemistry, usually you don't need to know how to do the integration, but I'm just going to write it out here for those of you that do like to understand the calculus behind it all. And starting with an equation like this, we could collect our A terms here and move this, divide by both sides and put it down here. And bring up the dt, multiply it by both sides to get an equation like this. And now this represents an equation that we can integrate. The left side with respect to A, the right side with respect to t. And you end up getting something that looks like natural log of A over A naught, once you collect some terms due to the property of logs, equals negative kt. Okay, again, what you really need to focus on is that this is a first order rate law, that it corresponds to this change, and that all of this integration in the end, you don't need to know how to do the integration usually, but all of the integration in the end leads to an integrated rate law. Okay, so that final line that I just wrote here, we can rearrange this further and sort of separate some things out to get us to this integrated rate law. And this is really the equation we're going to be using a lot in today's lecture. Natural log of A is negative rate constant times time plus natural log of A naught. And this A naught here, that naught means time 0. So that right there is essentially t equals 0. And we call this initial concentration. So how much reactant A did you start with? And generally we're preparing an experiment. Maybe it's 3 molar in A, and we start the reaction at time 0. That initial concentration is 3 molar. Okay, so that's what this A naught term means. And what we notice here is that natural log of A, we could represent as y. I'm going to write it out over here. Natural log of A is negative kT plus natural log of A naught. Okay, and we notice in a more familiar term, or form I should say, this looks like y equals mx plus b. Okay, the equation of a line. If we were to plot natural log of A on our y-axis, and if we were to plot time on our x-axis, then that data plotted should follow a linear relationship if this reaction is first order. And the slope of that linear relationship has a rate constant of negative k. So our rate constant is going to be positive. This data that we plot in this form is going to have a negative slope. And so the line that goes through here, when we plot it, the slope of this line is negative k, right? So you're going to get a slope out that's negative. Take the opposite to get a positive number. That's your rate constant. And so this is how we identify rate constants through experiment. We get the data, we plot it in this functional form, which we'll discuss further in a second. If it's linear, it's first order, and then we have the slope. The intercept here should be natural log of our initial concentration. So in this example we just discussed, if the initial concentration was 3 molar, then this y-intercept here should be the natural log of 3 molar. Okay, so let's see some data that actually looks like this. Here's an equation that ends up being first order. And here's the data. So let's imagine we actually run this reaction. And we have time here. We have concentration of our reactant, CH3NC. You can see in this reaction, let me write this a little bit smaller. It's a nitrogen and carbon that are essentially swapping places, forming a carbon-carbon bond when there was a carbon-nitrogen bond before. And so we have time 0, we might have 100 seconds, 500 seconds, 1,000 seconds. It doesn't have to exactly correlate to what's over here. I'm just sort of inventing some things, 5,000 seconds, 10,000 seconds, et cetera, et cetera. And we get some data here, right? We started with an initial concentration. Here it's a pressure, right? I guess this should be a pressure, not a concentration, but those two things are analogous, so it doesn't really matter for now. It's going to make the data look the same, whether it's pressure measured in torr or a concentration in molarity. Our initial pressure here is 150 torr, it looks like. Right? And then we have some other data here. If we plot this data that we've measured in the experiment, measuring this initial pressure or initial concentration, and it's going down in time, then this is what the data looks like. Okay, but that's curved, that is clearly not linear. And the important part here is that different reaction orders, this is first, but second order reactions also have data that might look like this. Third order reactions have data that might look like this. And so just from plotting the data, y versus x, concentration versus time, or pressure versus time, it's hard to differentiate first versus second versus third order. What we have to do instead is add another column here. And the other column here is going to be natural log of our concentration or natural log of our pressure. And when we get this, we take the data from this column and take the natural log of it and fill in this third column. And now what we do is we plot this third column, natural log of concentration or natural log of pressure versus time. And we get a graph that looks like this. And now it's very easy to tell that this is linear. And this is how we test first order behavior. Does the data we collected follow this functional form And instead of testing each data point by plugging it in, it's a lot easier to graph it and see if it's linear. So if the data looks linear, which it does here, we say, aha, this is first order, so the rate law looks like this. And we've identified this reaction as first order. We can get the slope here and say, aha, that's negative k. And now we have the rate constant and the rate law, which tells us something about the mechanism of this reaction. Now, if we went through and plotted this data and it wasn't linear, right, and it ended up being curved, then we would say this does not follow first order behavior. The rate law is not to the 1. Is it to the second? Is it to the third? Is it to the 0th power? We don't know, but we have other tests for that, which we'll discuss in future lectures. So this is from a practical point of view, how this is done. You collect the data, you plot it this way. If it's linear, it's first order. You've identified the rate law. Now, let's do some quantitative calculations with a practice problem here, using this first order kinetic equation, this integrated rate law, as we've called it, shown here, and see if we can answer this question. So feel free to pause the video here, take your time and work it out. Otherwise, I'm going to proceed with solving it. Okay, so let's read through this and try to identify all the particular types of information we have here. The decomposition of a certain insecticide in water at 12 degrees Celsius follows first order kinetics. So as soon as we hear that this is known, okay, we can write down a couple things, right? We can write down that, well, the rate is K times this insecticide that is decomposing to the first power, right? A decomposition reaction is one thing falling apart to some multiple things. So this is what the reaction looks like. The rate law we're told is first order, so it looks like this. And if it's first order, which we're told, we know it follows this integrated rate law expression for first order reactions. With a rate constant of 1.45 inverse years, okay? A quantity of this, that's K, so that's our K here, the rate constant. A quantity of this insecticide is washed into a lake on June 1st, leading to a concentration of 5 times 10 to the negative 7. Assume that the temperature of the lake is constant, so it doesn't affect, so that there is no temperature variation on the rate, so the temperature doesn't matter. What is the concentration of the insecticide on June 1st of the following year? Okay, so that's part A. So part A here is asking for what is the concentration at a later time, so the concentration of I after 1 year. That must mean this concentration here is our initial concentration, okay? So this here is our I naught, or in this case, as it's written down here, A naught. So all we're going to do here is take the data we're given and simply plug it in. Okay, what is the insecticide concentration later? Well, that is exactly what we're solving for here. ln of I equals negative 1.45. Okay, that's our value of K, inverse year. The amount of time is after 1 year. And now you can see why the rate constant has units of inverse year, plus natural log of our initial concentration, 5 times 10 to the negative 7 grams per cubic centimeter. Okay, and so now we can go through and plug in all our numbers here. The left side is still natural log of I. The right side comes out to be negative 15.9 something, maybe 9.6. And of course, we get rid of a natural log by taking e to the power of. So I is e to the power of negative 15.96. For part A, we get an answer of our concentration (1.2 times 10 to the negative 7 grams per cubic centimeter). Okay, so even though that looks like a density here, it's fine to plug it in here. We don't have to convert it to concentration. Whatever the units used here for initial concentration is going to be the same unit found here in our final concentration that we're asked for. So that's part A, the concentration on June 1st of the following year. Now, part B asks, how long will it take So what is the time for the insecticide to decrease to 3 times 10 to the negative 7? Okay, well, we're still going to use the same exact integrated rate law formula, only this time we have some different numbers to plug in. We're going to be solving for the time. How long will it take for the insecticide to decrease to 3 times 10 to the negative 7? Well, that is our later time concentration. So it's now, that is our A, that is our I, natural log of 3 times 10 to the negative 7 grams per cubic centimeter equals negative K, so negative 1.45 inverse years, times time, which is what we're after, plus our same initial concentration, right? We're still using, right, our initial June 1st measurement here, 5 times 10 to the negative 7. So you take natural log of that, you take natural log of 3 times 10 to the negative 7, you subtract them out, you divide by negative 1.45, and after you do all that algebra, the final time you should get is about 0.35, and the unit here is years, because that's what you were given for the rate constant. You can always move this into days if you want by multiplying by 365, and you get something like 126 days. So here I didn't ask for a certain unit, either would be an acceptable answer. Now, it makes sense that it's less than a year, 126 days, because we know from part A, after a year, it's at 1.2. So how long does it take to get to 3? It should be shorter than the amount of time it takes to decrease to 1.2. Remember, this reactant is constantly going away with time. So B, our answer would be 126 days. Another concept we have to discuss here is half-life. So we're still working with first order reactions, but a half-life applies to any rate law, any reaction order. Here we're going to solve it and discuss it in terms of first order reactions. But generally a half-life is the amount of time it takes for 1/2 of the reactant to be used up. Okay, this is in chemical reactions, but you can have half-lives of lots of things. In chemistry here, it's the amount of time it takes for 1/2 of the reactant to be used up. And the way this is derived is this 1/2 of reactant means you plug in for A, initial divided by 2. If there's 100 moles per liter, then when 1/2 of it is used up is 100 over 2, or 50 moles per liter. So that's what we're putting in for our concentration of A right here. The time we're going to call the half-life time. And now since we have natural log of A naught and a natural log of A naught, the property of logs suggests when you subtract natural logs here, you can combine them, divide them out, right? You get a quantity like this. The A naughts will cancel, and you'll be left with natural log of 2 equals KT. Right, so we've done some basic algebra here to get rid of our negative signs, to combine natural logs. I don't want you to get hung up really on the mathematical manipulation in the algebra, as much as the end result that our half-life time, the amount of time it takes to decrease the reactant concentration by 1/2, or cut that initial concentration in half, is 0.693, which is natural log of 2, 0.693 divided by the rate constant. And this is a really important result because it shows the half-life does not depend on your initial concentration. But again, this was derived for our integrated rate law for first order reactions, so it only applies to first order reactions. We'll see later it doesn't apply to second order or other reaction orders. But this is really interesting because it suggests for anything that obeys a first order rate law, that is a first order reaction, it doesn't matter if you start with 100 moles per liter, 200 moles per liter, 3 moles per liter. The amount of time it takes for half of that reactant to go away is always the same, 0.693 divided by the rate constant. Now, let's put this into practice and do a calculation here to calculate the half-life of this reaction. Feel free to pause the video here and try it for yourself before I solve it. Okay, the value of a rate constant for a first-order reaction. So if you were given a problem like this, reading first-order reaction, you need to remember, or I suppose derive, if you don't just remember it. You can always derive it from the calculus if you remember all of that. But you might be able to remember for first-order reactions that the integrated rate law looks like this, and you can derive the half-life. Or you can just remember as soon as you see first-order reactions, you know the half-life is 0.693, right? This thing we just derived right here, over K. So if we know the value of the rate constant, which it gives us, the half-life for the reaction, well, that's easy. It's 0.693 divided by 0.010 seconds. Okay, and then this means, well, the answer here should be 69.3 seconds. I rounded off to 2 sig figs here since this is actually 2 sig figs. But you should get 69.3. 1 over seconds to the -1 is just seconds. And so here is our half-life. Takes 69.3 seconds for this particular reaction to have its initial concentration of reactant cut in half. Let's try one more. If a solution containing 10 grams of substance reacts by first-order kinetics, how many grams remain after 3 half-lives? Tricky. Feel free to pause the video here and try it yourself before I solve it. So here you might see half-life and think, okay, T1 half is 0.693 over K, but I don't have a rate constant here. This is maybe an initial. So maybe you can think of first-order rate laws and write it out. And maybe you could determine that final answer somehow. But remember the definition of a half-life. Okay? After a half-life, half of the substance remains. So 10 grams after 1 half-life becomes 5 grams. After 2 half-lives, that 5 gets cut in half to be 2.5. After 3 half-lives, that becomes 1.25 grams. Okay, so this is more a conceptual question to make sure you understand what a half-life is. After 3 half-lives, the amount should be 1.25 grams. Okay, so that's half-life, integrated rate laws, and graphically what integrated rate laws look like for first-order reactions. As we move on, we'll cover second-order reactions, discuss all the same types of formulas, because first-order and second-order reactions really are the most common types. We'll also get to zeroth-order reactions as well. But that'll do it for this lecture. See you next time.